Okay, so like I said, I don't expect you guys to understand very much at all of what's been said so far. I just want you to listen to it, do your best to understand it, and we'll finally get to a point where you'll see that it's useful. So at least we'll walk down the path to the point where we found something useful, okay? Well, if we find something useful, I'll let you know, so you can go to sleep and do it. Okay? Anyway, we have to evaluate the entropy change for a closed system. So we're going to do that. To do it, we need to write an energy balance for the system. If this is a piston cylinder device, for example, that's a closed system, and we'll just write an energy balance where there's some small amount of heat transferred to or from the system, a small amount of, say, boundary work done, and a small change in the internal energy of the system. But remember, we can write the internally reversible heat transfer as TDS, and we can write the internally reversible work done as PDV. Now be careful. I just said something that should have made you go, wait a second, I didn't realize that before. A second ago, I said on a PV diagram, the area beneath the curve represents boundary work. And none of you really questioned me on that because you've seen it before. And you were just happy that I didn't make you do much of the integration. Maybe I made you integrate once in homework. Because you were very happy to have, the integrated form of PDV. But it turns out the area beneath this curve is only equal to the work if it's an internally reversible process. Think about it. This is actually pretty easy to show. You've done a lot of piston cylinder problems, right? Or at least you've worked on a lot of piston cylinder problems. Okay? What have we always said about the piston that allows us to calculate the boundary work that actually comes out of the system?
It's just floating there.
It's internally reversible. There's no friction. Okay. We also made the requirement that the gases do not expand quickly, because if they expand quickly, the pressure against that piston is going to drop, right? And you're not going to get as much work out as you expect. So when you say the area beneath the curve on a PV diagram is boundary work, that's only true if it's an internally reversible process. This is kind of interesting. We've used that so far and never really thought about it. But now that we're talking about entropy, and it seems more confusing, what is this internally reversible thing? Think of it as no friction, no mixing of gases, no fast expansion or contraction of gases. That's essentially what internally reversible means in the real world. Okay? Now, let's continue our derivation. That means we can plug in these for the inexact differentials and end up with exact differentials. Why are we doing all this? Who cares? Remember, the amount of heat transfer and the work that's done by or on a system depends on the path that system takes. We don't like that. We'd like to somehow write entropy in terms of just properties of the system. So that's where we're going right now. And we were started from the same point where we always start, in energy balance. Okay. So the equation comes down like this. If we move the work to the other side, it would be PDV, TDS would stay on the left-hand side, and DU is still on the right-hand side. Now we can write this in total form or in per unit mass form. So instead of capital S is capital U and capital V, we have a lowercase version. So this equation would work for both total variables and for specific variables. It turns out, even though we're talking about a closed system, this will work for an open system as well. Okay, so what we're about to derive relates entropy of a fluid flowing through a system to properties of that fluid as it flows through the system. So it'll work for both of these. Okay? Remember that enthalpy is U plus PV. If we take the differential of both sides of this equation, we'd have DH on the left-hand side, DU on the right, and then do you remember how to differentiate a product? You have to hold one constant, differentiate the second one, hold the second one constant, differentiate the first. Remember that from calculus? It's not kind of sort of maybe. Yeah. Okay, well, that's all that's been done. Okay. So then what did we do? Well, I have to think for a minute. TDS is du PDV. See how those two are the same? So if I were to write DH, I would get TDS substituted in there. See, we'll get rid of this du PDV in favor of TDS and leave the VDP alone. Okay? Now don't worry about all this derivation. It's not all that spectacular or anything. Now let's solve for TDS. Just move the DH, let's see. Just move the VDP to the other side. Flip it around. So we've got two different equations that allow us to talk about TDS in terms of enthalpy, internal energy, and volume and pressure. When we solve for ds, which is the only thing that doesn't really seem like a property of the system, we can write differential changes in entropy in terms of things that we know are properties of the system: pressure, volume, temperature, and energy. Okay? So, now, don't worry about these equations. You won't have to use them. We're going to use them to derive some other stuff. Okay? So you guys listen?
I was just looking at, so you kind of split the work into two separate things. Like you got TDS as part of the work and.
Kind of. Here's this PDV right here. Is this the part you're talking about?
Yeah.
Okay. Yeah, this PDV, all we did was we took a differential of both sides of the equation. That way, because we already had differentials up here, and we needed to plug in differentials. So the point here is that we get not just one, but two equations that relate entropy to properties of the system. Now, we will be very interested in entropy changes of solids and liquids. Well, for a solid or liquid, we could take this first equation, which involves internal energy, pressure, volume, and temperature, and we can make some substitutions, because remember, I had you guys write U equals CVT and H equals CPT in various forms, so that you would relate CP to H and CV to U. Okay? Well, du could be written as CDT. Now, why is it not CV or CP? It's because this is a solid or liquid. And for a solid or liquid, there's no boundary work, right? So it doesn't matter if we talk about heat capacity at constant pressure or heat capacity at constant volume. They're essentially the same thing. So we can just write this as CDT. So then what? Well, since we're talking about a solid or liquid, regardless of what process they undergo, unless they boil off or we burn them solid, there's not going to be a significant change in volume. So this piece would go away. So what we end up with, once we integrate this equation, how would we integrate it? Well, basically this term is gone. We'd have to integrate the entropy from one state to the next. We'd just get the change in the differential variable. We'd integrate this side from state 1 to state 2. We can't really simplify it any farther than this, okay, at least not initially. If we could say that the heat capacity was constant and did not depend on temperature, then we would have the integral of 1 over TdT, which is just the natural logarithm of the temperature. And once you evaluate the natural logarithm of the temperature at the temperature limits at state 1 and state 2, this is what you would get. Okay? Now, this is the first useful equation that you may want to start paying attention to. If you need a change in entropy for a solid or a liquid, here's an equation that would give it to you. When would you need a change in entropy? Well, I'll give you an example. Let's say I gave you a problem where heat is being transferred into some water. Okay, so heat is being transferred in, and we've got a certain size, volume, or mass of water. If you know the temperature at which that heat is transferred, you can actually calculate how much entropy was put into the water. If you knew, or if you wanted to find, though, the change in entropy of the water, you can calculate it as the average heat capacity times the natural logarithm of the temperature ratio of the water, where T2 is the final temperature of the water, T1 is the initial temperature. Now, what you would find, if you calculate both of these, you find that the amount of entropy transferred into the water via the heat transfer is less than the change in entropy of the water. Why would that be? Why would there be more entropy in the water than what was transferred in? Because heat transfer is irreversible. Make sense? And since heat transfer is irreversible, some entropy will have been generated. Yes, the water's entropy will change due to the temperature change, yes, the entropy of the water will change due to the heat transfer, but since this is irreversible, the entropy of the water will increase more than that. It will actually have some generated entropy in it. So that's a case where you might need to use this equation. What about what else could we do with this? What about an isentropic process? What if there is no change? What if we know that there is some kind of system that should have no entropy change across it? Such as what? Well, such as a pump. If you have a pump, ideally it would work best when there's no heat transfer and no friction, right? When it's reversible, okay? So in that case, the entropy change from inlet to outlet, from state 1 to state 2, would be 0. that means that this equals 0, right? Is the heat capacity of whatever fluid's flowing through it, is that where the 0 comes from? No, it must come from this term. How do you take the natural logarithm of something and get 1? What must that something be? 1, right? When you take the natural logarithm of 1, you get 0. So T2 over T1 must be equal to 1. In other words, T2 must be equal to T1. Now, what good does that do? Well, and I'll stop right after this. When I was at my first internship, Banjo Corporation in Crawfordsville, Indiana. It was about a 30-minute drive from where I lived at Purdue. Okay? My first internship, I would go there. They made mainly farm equipment, liquid handling stuff. So they made a lot of ball valves, they made pumps, they made all sorts of liquid stuff for farm equipment. Right? If you guys have any farm equipment, you probably are familiar with the product. Well, apparently they made pretty good stuff because everybody seemed to imitate it. You know, they had a lot of different ball valves that looked like their valves. It was interesting because one time one of the head engineers took me down to the coordinate measuring machine. He had one of the competitor's valves. He took it apart, put it on the coordinate measuring machine, took measurements and found that it was nowhere near as high a tolerance as their valves were. They had a pretty good product. Well, one of the products they made was pumps. And I was watching another engineer one time. I did some work there, believe me. I didn't just watch engineers do work. I was talking to another engineer, actually. He was testing some of the pumps they made. Now, if you were an engineer and you had to test pumps and you wanted to compare two pumps to each other, how could you do it? Well, you might look at the temperature change of the fluid as it flows through the two pumps. The one that has the lower temperature change is the better pump because it's closer to an isentropic pump. It has less internal friction, less turbulence generated, okay, so it's more reversible. Make sense? So this stuff does have practical application. I know we kind of have to plow through the woods, but once we get on the other side, there's a nice clearing. And this is one of the features of it. All right, anyway. We still have to play with those equations quite a bit more. We have to integrate them quite a few times, but we will do that later.